Good morning, good afternoon, good evening. Whenever you are watching this video, let me welcome you all to our channel Future Endeavors. Okay, so with all your support, I think we are going pretty well. I will be trying to give the videos more frequently, so please do support us in our endeavor. So, with those little words, let us quickly move on to our topic that we have been discussing. Okay, in the previous class, we have finished the chapter household circuits. Okay, today we will be starting a new chapter which is called the magnetic effect of electric current. Okay, so this is also an interesting chapter. I think we will be having fun learning this chapter. So let us quickly move on to the chapter details. Okay, so magnetic effect of electric current. Write down the heading. Chapter name: magnetic effect of electric current. Magnetic effect of electric current. Okay. So name of the chapter is magnetic effect of electric current. Okay. So from the name of the chapter, I think you might be having a little bit of idea of what we are going to discuss. Okay. So first of all, we will be coming to an experiment performed by Hans Ørsted. So what was the Ørsted experiment? Okay. So first of all, we will be discussing with the Ørsted experiment. In order to understand this magnetic effect of electric current, we will be first of all just describing an experiment which was performed by Hans Ørsted. Ørsted experiment. Okay. So what was the experiment? Just let us have a brief review. Okay. So what did Ørsted do? He took a wire. Okay, of say a certain length. We are not plotting the entire length. We are just looking at a part of the wire. Okay. Now he made current I, say I, to flow through this wire. Right. Now when current starts flowing, he took a magnetic compass. And kept it at the side of the wire. What happened? Now, when he kept the magnetic compass, the compass needle started deflecting as soon as the current started flowing. Okay. So there was a deflection that was observed in the magnetic compass. Okay, that's a deflection. Okay, now this deflection was shut off, or the deflection was not observed when the current stopped flowing. Okay. Now as soon as the current was switched off and made to flow in the opposite direction, say by reversing the battery source, the EMF source, that is the battery connected to the wire, the polarity of the battery is reversed. As soon as the current was reversed, it was observed that the needle of the magnetic compass also deflected in the opposite direction. In the previous case, it was being deflected on the right side. Now when the current starts flowing in the downward direction, what happened? The deflection was seen to be on the left. Okay, now the deflection seemed to be on the left. Okay, so the deflection was seen to be on the left. So like this, it was observed that the magnetic needle got deflected when it was kept near a current carrying conductor. Okay, so you can easily understand that a magnetic compass can only be deflected in presence of a magnetic field, in presence of magnet. So just keep aside the word magnetic field, just think of when it is kept near a magnet, because in general when a magnetic compass is held freely, it is observed that the magnetic compass points out in the geographic north direction, isn't it? So in general that is the deflection, there is no deflection, it directly points to the geographic north direction. But whenever it is brought near a magnet, you think I think you have seen it, or you may also do some experiment in your home with a magnetic compass and a magnet, that whenever the magnetic compass is kept beside the magnetic compass gets deflected from its normal position of pointing towards the north. Okay, so when we are saying, or when Oersted observed that when the magnetic compass is kept near a wire, current carrying wire, and the magnetic compass gets deflected, he concluded that so this wire, that the current that is flowing through the wire must be generating some kind of magnet, or isn't it? Only then it is possible for the magnetic compass needle to get deflected. And to ensure, means to further ensure this fact, what he did, when he switched off the current, the compass deflection was also stopped. So this quite easily proves that the current flowing through the wire must be producing some kind of magnet, isn't it? So this was mainly the Oersted experiment. Now from this Oersted experiment, what could be concluded? So from this Oersted experiment, what could be concluded? So Oersted experiments, from the Oersted experiments, the conclusions that can be drawn, what are the conclusions? First of all, whenever current flowing through a wire, behaves as a magnet. First thing, current flowing through a wire behaves as a magnet, isn't it? And it was observed that the more the value of the current flowing, or the more the magnitude of the current flowing, more the magnitude of the current flowing, more is the deflection. So more the current, greater the deflection. Okay, and with the reversal of the current direction, what happens? The magnetic poles are also reversed. That is why the compass starts deflecting in the opposite direction. So on reversing the current, the nature of magnetic effect also got reversed. Magnetic effect was also reversed, isn't it? Was also reversed. Okay. So just let us slightly tilt it down. Was also reversed. Okay. So these are the three conclusions that can be drawn from this experiment. Okay. So fine. So from this very experiment, it was ensured, or it was concluded definitely, that the current flowing through a wire generates a magnet, isn't it? Okay. Now let us quickly move on to what do you understand by a magnetic field. Okay. So I think all of you have read about the magnets and also the magnetic field in class 9. So we will just be having a brief recapitulation about the magnetic field and the magnet. Okay. So I think all of you have an idea about magnet, isn't it? Yes, obviously. Now what is actually meant by magnetic field? What is meant by magnetic field? So definitely it can be defined, or it can be stated as a region around a magnet in which the effect of the magnet can be felt. Okay, so the magnetic field can be stated that it's a region or area around the magnet where effects of the magnet can be felt. If we keep any other magnet in the vicinity of this magnet, definitely the magnet is either attracted or repelled, so it is being deflected. So, or if you keep any magnetic material in that region, in the vicinity of that magnet, you will see it will get attracted towards the magnet. So that region around the magnet where the magnetic effect can be actually felt is regarded as the magnetic field. Okay, fine. So I think you have understood what is magnetic field. Okay, now there are some lines which actually help us to indicate the magnetic field around a magnet. So what are actually magnetic field lines? Now the next thing that we will be discussing is magnetic field lines. Magnetic field lines. Now the magnetic field lines, these are actually imaginary lines that you can consider to be present around a magnet. These are imaginary field lines. Okay, these are imaginary field lines which you can consider to be around a magnet, along which the magnetic force seems to act. Okay, so if I just sum it up, I can say that these are imaginary lines around a magnet, along which the magnetic effect can be observed. Okay, can be observed. So these are the magnetic field lines. Okay, so magnetic field lines are actually they are imaginary lines, they are not present in real. Okay, so these lines actually help us to get the direction of the magnetic field as also the strength of the magnetic field. So if I just think of magnetic field lines, these lines you will see in a region of strong magnet, these field lines are quite close to each other, dense. But around a weak magnet, you will see that these magnetic field lines are not so close to each other, rather they are quite far away from each other. Okay, so magnetic field lines also help us to indicate the strength. So magnetic field lines, I think you have understood. I think that is one experiment that you might have done or read in your book, that if I keep a bar magnet, you have all seen a bar magnet. I think a bar magnet is nothing but a small piece of magnet which is a cuboidal shape, like this, something like this, a cuboidal shape. Okay, so as I am drawing it in 2D, so you will be viewing it as a rectangle, but it is actually cuboidal in shape. Okay, fine. Now if you keep this magnet over a cardboard and put some iron fillings all around the magnet and gently tap 2 to 3 times, you will be seeing that these iron fillings align themselves along certain lines from the north pole to the south pole of the magnet. Those lines are actually called the magnetic field lines. So you can understand that those are the lines along which the magnetic field is actually working. Okay, so these lines seem to be like this. They start from the north pole and end up on the south pole. Start from the north pole and end up on the south pole. Okay, like this. So these are the magnetic field lines. Okay, so the direction is from the north pole towards the south pole. Okay, from the north pole towards the south pole. Okay, outside the magnet. And if you consider, we actually cannot see inside the magnet, but it has been experimentally found out that inside the magnet these magnetic field lines are from the south pole to the north pole. Okay, so these are the magnetic field lines, or these are the magnetic field lines that you can observe around a bar magnet. Okay, so these are the magnetic field lines. Now if you just think of what are the characteristics of magnetic field lines, I think you have also, some of you may have also read this about magnetic characteristics of magnetic field lines. So I have also already mentioned few of the characteristics, that magnetic field lines start from the north pole of a magnet and end on the south pole outside the magnet. That is, outside the magnet they are running from north pole to south pole of a magnet, and inside the magnet they are actually running from the south pole to the north pole, the reverse. Okay. Also, what other characteristics you can observe, that magnetic field lines are actually continuous lines, continuous curved lines. They do not show any break. Okay, so actually these lines will continue from the outside, like this. Okay, these lines will continue from the outside, like this. That is also a line here. Okay, so this lines will continue from the outside, so that without breaking these lines continue. Okay, again, for a strong magnet the magnetic field lines are dense, rather very close to each other, whereas in case of weak magnet the magnetic field lines are far away from each other. Please note down these points. If you have not noted it, please just pause the video or just rewind, move back a little bit and note down the points. Also, the magnetic field lines, as you know, the strength of a magnet is greatest at its poles. For a bar magnet it is greatest at the poles. Hence the magnetic field lines are most dense near the poles, and at the middle the magnetic field lines are actually far from each other. In the middle the magnetic field lines are actually far from each other. Okay, so like this they will start drifting away from each other. Okay, and the magnetic field lines, two magnetic field lines never intersect each other. Remember this point, is very important. Two magnetic field lines never intersect each other. Magnetic field lines never intersect each other. Why? Can you answer this question? I think some of you may have also read this. This is because on a point on the magnetic field line, if you draw a tangent, say I am considering this point. So if I draw a tangent at this point, this tangent gives me the direction of the magnetic field at that point. Okay. Now if I consider that two magnetic field lines have intersected, say like this, two magnetic field lines have intersected. One goes from this direction to this direction, another goes from in this direction. Now if I consider these two magnetic field lines, then at this point I can draw two tangents. One is this direction and one is this direction, gives this direction of magnetic field, and this tangent gives this direction of magnetic field. So at a single point you are getting two directional magnetic field, which is not actually possible. Whenever two magnetic field lines interact at a point, there is a net magnetic field, and accordingly there is only one directional magnetic field. So two magnetic field lines never intersect each other. So these are the properties of magnetic field lines. Okay, so the characteristics of the magnetic field lines that have been observed for a bar magnet, those same magnetic field lines can also be observed for a current flowing through a wire. As because a current flowing through a wire behaves as a magnet, they will also produce same kind of lines. So we will be discussing this topic on the next class, that is the current magnetic field due to a current. Today we will be stopping our lecture here. Okay, I think the topics that we have discussed is clear. So hopefully we will be seeing you on the next video. Till then, thank you, take care, goodbye.